Thank you very much. First of all, thank you very much for the invitation. It's really nice to be here. I've obviously never been to Mondovì before. And also, I've already learned quite a bit at this school. So I have to apologize that my talk is not directly related to topoi, but at least I hope that it's somewhat tangentially related, so that people can, well, connect what they are interested in with it, with the subject of my talk. All right, so just to give you an overview, I'll spend the first 15 minutes explaining some things about geometric Langlands and what it is that I want to do. Then it'll be a big chunk about Fourier transform, and then the last 15 minutes will be again about, we'll come back to geometric Langlands. So that is to say that if you're not interested in geometric Langlands, feel free to go to sleep for 15 minutes. All right, so now without further ado, let me give you the context. So we work over a ground, so yeah, we are in algebraic geometry. We work over a ground field K of characteristic 0. So X is a curve, smooth complete curve over K. G is a reductive, well, semi-simple group over K, and G check its Langlands dual. So if you've never heard of Langlands dual groups, it's okay, just you won't get this next 15 minutes. All right, so what do we want to study? Our first, so Langlands correspondence has two sides, geometric and spectral. On the geometric side, we consider the following geometric object. We denote it bun G of X. It's the moduli stack of principal G bundles on the curve X. And then we'll do something with it. And then I'll say in a minute what we'll do with the spectral side. By the way, I really encourage people to interrupt me and ask questions. And you should know that the stupider the question, the better. So, like, if you really have a stupid question, go ahead and ask me. All right. So before I go further, let me make a short detour about prestacks. So prestacks are functors are just contravariant functors from category opposite to affine schemes to infinity groupoids. So first of all, when I talk about affine schemes, I am in derived algebraic geometry. So an opposite category opposite to affine schemes, it is the category of what we call connective commutative rings over the ground field K. So because K is assumed characteristic 0, like, there are no complications. You can think of it as simplicially or just really kind of differential graded algebras in non-positive degrees. So I should also say that these functors are, there are some set theoretic words to say which I'll completely ignore. Presentable, accessible. I learned what these notions are and then I immediately forget. So some kind of nice functors. So anything under the sun in algebraic geometry is a prestack. Schemes are prestacks, stacks are prestacks, formal schemes. So basically, like any object in algebraic geometry is a prestack, and then you put conditions, not extra structures on it. So if you have a prestack, you can characterize it like when it is a scheme or when it's a stack or something like that. So now, if you have any prestack whatsoever, you can define the category of quasi-coherent sheaves on it. And so you define it as follows. So if Y is a prestack, quasi-co of Y is defined as follows. So informally, what you say is this. For every affine scheme that you map to your prestack, you specify the pullback of your quasi-coherent sheaf on your affine scheme. And that things should be compatible with compositions. And formally, you write it as like this. It's the limit over the category of affine schemes. I'll write it as mapping to Y. And again, to specify maps to Y, by definition, is the same thing as to specify the value of your functor on S of quasi-co on S, where the transition maps are pullbacks. So again, just the way you have to think about it, I just repeated what I just said. A quasi-coherent sheaf on Y is completely determined by its pullbacks to all affine schemes, and these things should be compatible in a natural way. All right. So now, so there's some important pre-stack to keep in mind. So if you have a pre-stack Y, you can create from it another pre-stack. So actually, it was Grothendieck's idea to do it, called Y de Rham, and it's defined as follows. So hom from an affine scheme S to Y de Rham is the same thing as the hom from S reduced to the original Y. Where S reduced is that, again, remember S is the spectrum of a connective ring. You kill all the lower cohomologies and you also kill all the nilpotents. So like you should think of Y de Rham as the quotienting Y out by the infinitesimal groupoid. And so one uses the following notation. So D modules on Y is by definition quasi-coherent sheaves on Y de Rham. So this is really a definition, but then you may wonder does it have to do with D modules as we know them. So like if you have a smooth algebraic variety, we kind of know what D modules are. And it's a theorem essentially due to Grothendieck, who explained that this definition really reproduces D modules. So like you should think of D modules, like one way to think of D modules is really quasi-coherent sheaves on Y, equivariant with the spectrum infinitesimal groupoid. And this is what this definition achieves. All right, so why did I mention all of this? Is because in geometric Langlands, this category that we study on the geometric side is D modules on G. And so again, when I write quasi-co, I really mean the infinity category. I never mean an abelian category. So this is the gadget lives in higher categories. All right, so now what about the spectral side? So we introduced the following object. So let me just rewrite what Bun-G is. So Bun-G is actually the mapping pre-stack. So you consider maps, let me call it underline, meaning I'm taking the internal hom from Bun-G of X, mapping pre-stack from your curve X to the classifying space to BG. And now we introduce another guy. Let me write it here. I'll call it, it's the pre-stack of local systems. So I call it LS for local systems with respect to G check. And that's the mapping stack from X de Rham to BG check. So, and again, because of what I said about D modules, you can think that you can verify that points of this thing is really local systems with respect to G check as you may naively know them. And so we have, it's another geometric object, it's a pre-stack. It happens to be an algebraic stack, but we don't really care. And what we do, we take the category of quasi-coherent sheaves on it. And so to be honest, one has to modify it a little bit, but that's completely irrelevant for this mini course. And so geometric Langlands predicts an equivalence. So just note the symmetry here. So this Bun-G didn't involve anything de Rham, but we took D modules on it. And so this here, the stack of local systems has de Rham inside, but then we take kind of usual quasi-coherent sheaves on it. So that's the statement of geometric Langlands. So it's now a theorem. And so what I'm going to explain in the next 5 minutes, there was a tiny glitch when you tried to prove it. And this glitch kind of unleashed this theory of two Fourier multiplier transform. So basically, we proved it by a trick, and this trick works really well when G is adjoint and G check is semi-simple. And when G is semi-simple, like SLN, you'll see why, like, we lose a little bit control. We needed to know a little bit more, and that a little bit more is what I'm going to talk about. All right, so let me tell you the nature of this a little bit more. So let's look at the center of G. So we said that G is semi-simple. It's really a finite group. And note that this group acts by automorphisms of every point. So like if you have a G bundle on anything, the center of G acts by automorphisms. And so what happens is that, so this group acts on the category of D modules. So let me just say it very concretely. So if you take, so let me fix a point Y in bund G of X. And if you have a D module, let me so it M, it's an object of the category of D modules on bund G. You can take its fiber, it's a vector space, but what I said about the center acting means that it's not just a vector space, the group ZG acts on it. It's a representation of the group ZG. And if it's a representation, you can decompose it with respect to characters. But you didn't have to fix a point, it happens just globally over bund G. So what this is intended to say is that the entire category, D modules on bund G of X, splits as a direct sum indexed by characters, let me call them chi, of center G dual. So this means Cartier duality, really kind of the group of characters of our finite group of categories that I'll denote this way. D mod bund G of X sub chi. So this is the full subcategory, direct sum and on which my center acts with respect to according to the given character. So now let's see what happens on the Langlands dual side. So there we have the geometric object log sys G check, and so you can use whatever geometric intuition that you have, that so if this group is not simply connected, local systems or bundles, they have a first Chern class, and this Chern class lives in pi 1 of this group. So one can say that like pi 0 of the stack, that in fact is isomorphic to pi 1. So let me just make a distinction here. I call pi 1 algebraic of G check. So what do I mean by pi 1 algebraic? So you have a semi-simple group. You have, let me call it, this is the, what do they call it? There is a weight lattice. And so there is a root lattice. And so pi 1 algebraic is the quotient of one by another. So rather, I should have said mixing the group with the dual. It's a quotient of the root lattice by the weight lattice by the root lattice. So, like in the example, so if our G check is PGLN, this is the example to keep in mind. Pi1 algebraic of G check is the group Z mod n Z. And I just want to emphasize the distinction between pi1 algebraic and pi1, the actual pi1. So like the actual pi1 of G check, you have to apply the Tate twist, what we call of 1. So you tensor over Z with roots of unity. So just to explain this point here, so pi1 actual of PGLN is mu n, is the group of nth roots of unity. So, and there is a map like this, which you can, so a convenient way to view it is as follows. So here is your group. This is, so this is the simply connected cover. And here the kernel is the actual pi1, not pi1 algebraic. So, and so if you have a local system or a bundle, so if you have a point of H1 on the curve with respect to G check, and by the long exact cohomology sequence developed by Giraud in this non-commutative context, so it goes to H2 with coefficients in pi1, but if you remember from the first course on the Tal cohomology, H2 of the curve with coefficients in a finite group is the Tate twist of this finite group, negative Tate twist. So this is pi1 G check of -1, which is exactly pi1 algebraic. So that is to say that we have this bijection. So our geometric object splits into connected components, and therefore the category, so quasi-coherent sheaves on this geometric object also splits into, let me call them chi tilde. So these are elements in pi1 algebraic G check of so just I split my category of quasi-coherent sheaves according to connected components. And so now let's notice that if you think of definition of Langlands duality, the Cartier dual of the center of G is exactly this group. It's pi1 algebraic of G check. So here's an example. So if G is SLN and G check is PGLN, so the center of SLN is mu n, and its Cartier dual is really maps from mu n to mu n, so it's Z mod n Z. So it's like pi1 algebraic G check is Z mod n Z, as it should be. All right, and so here is the theorem, is that with respect to the geometric Langlands decomposition, we have, so these two decompositions into direct summans match up. So like chi corresponds to quasi-coherent sheaves on the corresponding connected component, where chi and chi tilde correspond to another to one another under this bijection up to a sign. And the second point of the theorem says that there is no human being who can keep track of this sign. So it's Right, so this is what you want to prove. And now I'll make a kind of long detour of how. So what you have a priori, you have a functor in one direction, and you want to show that this functor in one direction sends this direct command to this direct command. And now I'm going to build a very big machine to prove this thing. And it's kind of non-obvious. So if you've thought about automorphic functions, like SLN is complicated exactly because of the presence of the center. And it's hard to lay your hands on it. All right, so that was my detour about geometric Langlands. You can safely forget about it for the next 2 hours and 15 minutes. And so now we launch into this discussion of Fourier transform. So yeah, I have to give a warning. So 2 years ago, I lost a teaching job. And the reason was that I tortured my students. And the way I tortured them, I asked them questions. And so the organizers were imprudent enough to invite me. Little did they know that all I want is my little revenge. So I'm going to ask you questions. All right, Fourier transform. So again, we are in algebraic geometry. Let A be a commutative pre-stack. And in this case, you can define its dual. It's the mapping pre-stack from A to GM in the commutative world. So as commutative group pre-stack. Commutative group pre-stacks and maps as commutative group pre-stacks. So of course, nobody told you the double dual is A, but let's assume that. So examples. So here are the basic examples. If A is Z, question to the audience, who is A check? Who knows how to classify commutative maps of commutative groups from Z to anything? I'm not going, somebody has to answer this question. So A check is GM. Great. Okay, if A is GM, who knows how to classify scheme theoretically maps from GM to GM? They are the powers. Scheme theoretically, you cannot deform them. It sits discretely. All right. That's great. All right. Okay, let's make it a little bit more complicated. A is an affine space. I call it V, really vector group. So can you map a vector group like something like GA into GM? Yes or no? No. Okay, so what do you say? A check is what? No. You can, the physical points are just one point, but infinitesimally you can. So A check is you take the dual vector space and you take its formal completion of the origin. And similarly, if you take A to be this, then A check will be V. So they're actually in perfect duality. So like the actual vector space gets replaced by the formal completion of the dual at the origin. And if A is a finite group, what's A check? Finite abelian group? Somebody? Not Laurent, someone else. Hey guys, classify homomorphism of finite abelian group into GM. Hint, it's already on the blackboard. All right, I give an answer, but that's last time. So really, my question must be answered. So it's the Cartier dual. Like if you want to classify homomorphisms from UN into GM, they're all, it's Z mod on Z. They're all powers of the standard embedding. All right, where are we? All right. So let's do Fourier transform, just to start. So we want to do two Fourier transform. We'll first do zero Fourier transform, like usual Fourier transform. Then we'll do one Fourier transform. Then we'll do two Fourier transform. But let's start with zero Fourier transform. So if you have an algebraic variety, I'll write fun of y, just because I want to have fun. It's the global functions. So suppose I have like A and A check, and I want to define Fourier transform as we know it. I'll call it Fourier Mukai 0 from functions on A to functions so most of you were in undergrad not so long ago. Does somebody remember, and I know that you started doing category theory, but does anybody remember the definition of Fourier transform? Like a function goes to where? Somebody give me an answer.
Maybe the direct product of the homomorphisms.
Come on, remember the formula, like Fourier transform from R to R.
Yes.
There are no endomorphisms there. Like it was remember they e to the xy integral.
Yes, fx and e to the minus ix.
Right, and then what? So the value of this at the character chi is what? Let me call it point A check. So I start with a function on A, I want a function on A check. So what is it? So I integrate f of A int what?
So you take the function on A, you put it back
Yeah.
A cross HH,
And
multiplied by the natural character A cross HH, and you integrate on A.
I understand everything apart from the word integrate. What do you mean by integrate? It's like Riemann integral, Lebesgue integral, what kind of? Doesn't work. So in algebraic geometry, not defined. So the best you can hope for is the following. You can, if you think of it, you will be able to define a map from the dual vector space of this to functions on A check. Because there is no integral, like you really cannot map functions to functions. You can map dual.
Replace functions with sheets, and then you have an analog of integration.
So that's exactly where we're going. Not quite though. All right, so this kind of works. And so you can look at these examples, and it's very beautiful. It will work one way, but not another way. So like if you take the dual of the functions on GM, it will exactly match the functions on Z, but not the other way around. And if you take the dual of functions on this, it'll match exactly the functions here, but not the other way around. So like it really kind of works pretty badly. All right. But we know that things become better if you really raise the level of categoricity. And there is a reason for it. And the reason is that as you go higher in this hierarchy, things become more dualizable. Let's spend a minute about this. So, what is the world in which we live? Question to the audience. It's called DGCAT. So if you wish, it's stable infinity categories linear over my ground field K. There are plenty of ways to define it. So the main thing is that this category is a symmetric monoidal category. If you have two DG categories, you can tensor them together. It's called Lurie tensor product. You have C1, C2. You can create C1 tensor C2. And it's very much in the spirit of Szysinski's talks. Like, you don't really have to know what it is. You have to know that it exists. It's an allowable phrase to tensor two categories together. But I give you an example. So if you have two associative algebras, A1 and A2, here's what happens. If you take A1 mod, it's the DG category of modules for A1. If you tensor by A2 mod, this is really isomorphic. So the definition is rigged so that it's isomorphic to A1 tensor A2 mod. And so, in particular, for a pair of affine schemes, quasi-co S1 tensor quasi-co S2 is the same as quasi-co of S1 times S2. So, it's just a particular case of this. So now you can ask the following general question. If you have two pre-stacks, there's always this external tensor product functor from quasi-co Y1, quasi-co Y2, wrote it badly, to quasi-co on the product. And you can ask, is this functor always an equivalence? The answer is not in general, but it's very hard to come up with an example where it isn't. So in all the pre-stacks that you're likely to encounter, this is an equivalence. So for all practical purposes, it is. All right. Where was I? All right. So, because it's a symmetric monoidal category, one can talk about no objects being dualizable. And so if you look at the definition of what it means for a vector space to be dualizable, it's really categorical notion. So whenever you have a monoidal category, an object can be left or right dualizable. If it's symmetric monoidal category, left and right don't matter. And so what's a duality datum? So if you have two categories, to specify duality, you have to do an evaluation map to the unit object. So the unit object in our symmetric monoidal category is vect. It's the DG category of chain complexes of vector spaces. So it's called evaluation map, and there must be a unit map that satisfies the usual axioms. And what happens is that most of the DG categories that you encounter in practice are dualizable. It's very hard to actually produce a DG category which is not dualizable. So here's an example. So if C is A mod, or an associative algebra A, then the dual category happens to be modules for the algebra with the reversed multiplication. So here is how these arrows are constructed in this example. So that the evaluation functor is the following one. So you take A mod, so it goes like this. You take an object in C, you take an object in C dual, and you take their tensor product over A. So let's say M was a right module, N was a left module. It's exactly a module for the opposite algebra. It makes sense to take their tensor product over A, and you get a vector space. That's your evaluation map. And the unit map, so I have to create an object in A tensor A op mod. We said that that's the same thing as a bimodule. It's a module for A tensor A op, and it's the following one. So evaluation sends the unit vector space to A viewed as a bimodule. So that's how it works. So why did I mention this? So let's translate this procedure into algebraic geometry. So in this case, A is commutative, and so there's no difference between A and A op. And basically what this shows is that the category of quasi-coherent sheaves on an affine scheme is self-dual. And let me rewrite what I wrote here in using the algebra geometric language. So I have to tell you what this evaluation functor is and what the unit functor is. So here's what they are. You start with quasi-coherent sheaves on S tensor itself. We identify it with quasi-coherent sheaves on S times S. So this operation of tensor product is, in the algebra geometric language, is pulled back to under the diagonal morphism. And then you take global sections. You forget the action. So it's global sections. And so this functor, you go backwards along this diagram. You start with vector spaces, which is the same as quasi-coherent sheaves over a point. You apply the pullback functor to quasi-coherent sheaves on S. And then you apply direct image functor with respect to the diagonal. And then you identify it by what we call the categorical unit formula. So the point of me writing this is that the same thing works for arbitrary pre-stacks as long as these operations are defined. So, and what you really have to pay attention to is that, so pullbacks are always well defined. The problem is with this push forwards. So like here I've taken global sections, and if your scheme is, let's say, is not quasi-compact, just push forward is a bad idea. So like you really want to take push forwards with respect to morphisms that are schematic and quasi-compact. So it will work, again, if your stack is nice enough. All right. So with this introduction, let's do Fourier-Mukai transform as we know it. So I leave this aborted attempt at usual Fourier transform. I'll again start with a group, an abelian pre-stack A, but now A check, well, maybe I'll call it A1 and A2. So A2 will have a different meaning. So A2 is the mapping pre-stacks inside as a commutative group pre-stack, but not to GM, but rather to BGM. So if you wish, it classifies line bundles. So points of A2 classify line bundles on A1 that behave multiplicatively. So, and in this case, you have the evaluation map A1 times A2 going to BGM. So again, this relationship doesn't have to be involutive, but let's assume that it is. So what are the examples? It's examples from the same list. So basically, if you start with what we had before to GM, you can create such a situation by replacing one of the factors with its B. So this gives rise to B A1 prime to BGM, or also A1 prime times B A2 prime to BGM. And if this was a perfect pairing, then so are these. All right. And you can think, by definition, what's the map to BGM? It's a line bundle of the product. You can call it the Poincaré line bundle. All right, so let's try to do Fourier-Mukai transform. As Laurent said, it's we can integrate in algebraic geometry, but let's try. So I want to define a functor from quasi-coherent sheaves on A1 to quasi-coherent sheaves on A2. So here's my working space. So again, I can think of this functor as a line bundle of the product. Who remembers the formula for Fourier-Mukai transform?
Yes, I think that here most people don't know the classical Fourier-Mukai.
Okay, then I'll teach them. So here's the formula. You go from A1 to A2. So here is your A1, A2. It has two projections, P1, P2. And I ran out of space because I want this example. Okay, let me just raise the blackboard. So Fourier-Mukai transform is defined as follows. Fourier-Mukai of a sheaf F, you do the following thing. You pull it back with respect to the first projection, and you tensor it by this Poincare line bundle that we said exists on A1 times A2, and you push forward with respect to P2. So that's the classical definition. However, there is still a problem. The same problem with integration. So you're pushing forward with respect to P2, it's direct image with fibers that look like A1. And it's only a good idea if A1 is nice enough. So like to do this definition, you really have to assume that A1 is a scheme or something like this, or a stack. You really don't want to do it even when A1 looks like Z. That's a bad idea. So this formula is kind of valid, but only when A1 is a scheme or on a scheme or a stack. What the actual Fourier-Mukai transform does, it actually defines a functor from quasi-coherent sheaves A1 dual category to quasi-coherent sheaves on A2 in the same way as we had with Fourier transform. Now, if you're lucky enough, if you can identify this category with its own dual, you'll get the Fourier-Mukai transform as you know it. But not always. So let's look at some examples. So here's one pair of examples. So let me start with GM, and here it will be, according to what I wrote here, it will be BZ. Actually, let me start with BGM and Z. So we're going to have a functor from quasi-coherent sheaves on BGM into quasi-coherent sheaves on Z. So what are quasi-coherent sheaves on BGM? In fact, for any group quasi-coherent sheaves on BG, these are representations of G. And representations of GM are really vector spaces graded by characters, the Z-graded vector spaces. And what are quasi-coherent sheaves on Z? What's a quasi-coherent sheaf on Z? You have vector space for each point of Z. And you can, if you unwind this definition, you'll see that this functor is really kind of the tautological equivalence. Like Z-graded vector spaces go to Z-graded vector spaces. So like this example parses. It's great fun to work out the other examples that I wrote from all this list. I won't do it now, but it's kind of, if you really want to understand how things work, do those examples. Just the warning that if you try to go the other way, this particular formula is not good because you don't want to take the direct image along Z. So you have to do something else. There will be another way to identify quasi-coherent sheaves on Z with a dual, but not given by this procedure, given by a slightly different procedure. So I really encourage people to do this exercise for vector space and for the completion of the dual vector space of the origin and see what happens. So what's really important for us is the case of finite groups. So let's have a finite group gamma, and its dual will be B gamma dual. And so Fourier Mukai will, let me write B gamma and gamma dual. So, as I wrote before, quasi-coherent sheaves on B gamma is really representations of the finite group gamma, and representations and quasi-coherent sheaves on gamma check are, let me write it, vect gamma check. These are vector spaces graded by the elements of gamma check. It's really, here you perceive gamma check as a discrete set, so you have a vector space at each point. And the equivalence you get, you can call it Fourier transform. It's really representations of a finite abelian group. They decompose according to characters. So this is the equivalence you get as your Fourier Mukai. So this is how Fourier Mukai works in elementary examples. However, I should mention one more thing, which is so I promised to teach you Fourier Mukai transform. So it was invented not for these kind of games. It was invented for something else. Examples that do not come by taking B of something. So the main example is that when A is an abelian variety, and in this case, A check is what's called the dual abelian variety. And it's defined exactly like I wrote there. It's the mapping space of multiplicative line bundles on A. And in this case, you obtain an equivalence from quasi-coherent sheaves on A to quasi-coherent sheaves on A dual. And it's called the Fourier Mukai transform. That's how it was discovered. So like this is the really main example. All right. All right. So what we have done so far, we've made an abortive attempt of Fourier transform. I've defined what Fourier Mukai transform is. And next, I'm going to define what 2 Fourier Mukai transform is. So, but that goes into the next level of abstraction. So far, we dealt with the categories quasi-coherent sheaves. 2 Fourier Mukai transform deals with not quasi-coherent sheaves, but quasi-coherent sheaves of categories. So that's the next thing we have to discover. And again, I hope that this will be close to the hearts of people who are interested in topoid, because like it's very much in the spirit. However, I propose to make a break. So like I have like 2 hours straight, right? It's like from 2 to 4, right? Yeah. So let's make a whatever 10-minute break and then come back for the next dose. So the next topic is sheaves of categories. So let's Y be a pre-stack. I'm going to introduce a 2 category denoted sheaves of categories over Y. And it's the following thing. So let me tell you what its objects are. So a sheaf of categories let me denote it C underlined over Y, is the following assignment. So for every affine scheme S mapping to Y, just as we did with quasi-coherent sheaves, to it, I assign a category, let me call it like, so it's an affine scheme and point little y. So the category depends on S and on Y. It's a category, but which is a module category for the monoidal category of quasi-coherent sheaves on S. So it's very closely mimics the definition of quasi-Eulerian sheaves. In quasi-Eulerian sheaves, for every such guy, I attached a vector space on which functions on S acted. And here I'm just going one categorical level up, and I attach a category on which the category of quasi-Eulerian sheaves on S acts. Plus, one imposes compatibility conditions, again, very similar to what one does for quasi-Eulerian sheaves, as follows. Suppose you have a commutative triangle. So this is little y1, this is little y2. So on the one hand, you have C S1 y1, and on the other hand, you have C sub S2 y2. So this is a module category for quasi-co S1, and this is a module category for quasi-co S2. How are they related? Well, in the case of sheaves, we tensored up, and we do the same thing here. So you impose that this is so we are doing tensor product over a commutative ring in this Luris category of DJ categories. So like you can really do algebra there, and so that's what we're doing. So, and then you impose this system of compatibilities, and so the machine of higher categories allows us to do that. So that's a definition of a sheaf of categories. All right. So let me give an example right away. So let G be a group pre-stack. Let me describe more explicitly what are sheaves of categories on BG. So on BG. So this is a question, and here's an answer. So you think of BG simplicity. So you have point, and then there is point G, and then G squared, and so on. So if you have a sheaf of categories in BG, the first thing you do, you evaluate it on S, which is point. And you just get a category. And then you have to supply all the datum that kind of creates the simplicial object from it. So the point is that, so the sheaf of categories in BG is the following datum. It's a DG category C with an action of G. Now, let me explain to you what this means. So this is some very natural notion in algebraic geometry. So if you have abstractly a category and abstractly a group, there is a natural notion of a group acting on a category. In fact, group can act on any object. But here's what you do in algebraic geometry. So again, what you do is the following. So an action of a group on a category is the following assignment. For every affine scheme S, you consider the following objects. You consider your category C, and you tensor it with quasi-coherent sheaves on S on the one hand, and it's a category which is linear over quasi-coherent sheaves on S on the one hand. On the other hand, you can consider HOM from S to G, and that's a group. And what you do, you make this group as an abstract group act on this category in a way which is quasi-S linear, compatible with all the pullbacks. So like that's a, again, very Grothendiekian definition of action. You do something for every affine scheme compatible with pullbacks. So that's what it means to have an action of a group pre-stack on a category. And again, if you unwind the definition of sheaf of categories, you'll see that. So this is exactly what it means to have a sheaf of categories. And so here you can add the additional remark that if G is an affine algebraic group, then, so you can simplify it a little further. So an action of G on C is the same thing as the following. You can consider quasi-coherent sheaves on G as we know it, and you can make it into a monoidal category under convolution. So the group operation on G, direct image with respect to it, defines a monoidal structure on G. And so you view it as a monoidal category under convolution. Let me put a little star. And so this action, the way I defined it here, you can actually rewrite it as an action of this monoidal category on C. So that's example number 1. And there's another example that I would like to consider. So what is a sheaf of categories? Over, so now we're getting more and more abstract, over B squared gamma, where gamma is, let's say, finite abelian group. So let's unwind this definition. So we said that on the one hand, this is a category acted on by just B gamma. But according to what I said over here, well, B gamma is not exactly an affine algebraic group, but it behaves like such. So it's the same as a category acted on by the category of quasi-coherent sheaves on B gamma, but under convolution. And now let's remember that we had Fourier-Mukai transform at the end of the previous hour, which said that this is equivalent to quasi-coherent sheaves just on gamma check. But note that Fourier transform exchanges convolution with pointwise tensor product. And this category, again, this is just really vector space is graded by gamma check with pointwise tensor product. So the upshot is that this is the same as, let me call it vect gamma check. So these are categories just graded by elements of gamma check. So again, a sheaf of categories on B squared gamma is the same as a category graded by vect gamma check. All right. All right, so now there is an important notion associated with sheaves of categories, and it's the following one. So let me maybe erase here. So you can consider the following thing. You can consider the two category of sheaves of categories of Y. It's a two category, but then there's another two category you could consider. It's the following. You can consider the category of quasi-coherent sheaves on our pre-stack. And it's a monoidal category, and you consider modules over this. So you should kind of, in the back of your mind, you should keep the analogy between quasi-coherent sheaves on Y versus modules over the algebra of functions. So remember, here we have the functor of global sections. If you have a quasi-coherent sheaf, you can take its global sections on Y and obtain a module for the algebra of functions. And something similar happens on this higher categorical level. So let me call it boldface gamma on Y. And you can create a module category for quasi-coherent sheaves. So what is this boldface gamma? So if you start with this sheaf of category C, boldface gamma of it, so it's just like you form global sections. You take compatible families of global sections. It's the limit over all this S comma Y of the categories that we denoted S little y. So, and each one of these is acted on by quasi-coherent sheaves on S. So therefore, when you take the limit, it will be acted on by this limit, and the limit is exactly what we denoted, how we defined quasi-coherent sheaves on Y. So if you have a sheaf of categories, you can take its global sections, and it will be a category on which quasi-coherent sheaves on the pre-stack act. So now definition, Y is one affine if gamma is an equivalence. So it's evidently an equivalence if Y was an affine scheme, but so as usual, when you increase the categorical level, such properties improve. So it turns out that there are many more pre-stacks that are one affine than just affine schemes. So there is a general theorem that says that any quasi-compact algebraic stack is one affine. And in fact, so a lot of things that are one affine. So now we'll draw some consequences of this theorem. So let G be an algebraic group. And let's take Y to be BG. This is your most basic algebraic stack. So in particular, this theorem says that it's one affine. So the corollary, we obtain the following, is that so there exists an equivalence between, so here is the two category of categories acted on by G and the two category of module categories for representations of G. So explicitly, if you have a category acted on by G, so the way this arrow goes, you assign to it the category of G equivariant objects. And by construction, it gets acted on by G equivariant objects in vect, which is exactly representations of G. And so it's It's not a very hard theorem, but it's a very useful theorem. It tells you that if you have a category in which a group acts, you can completely recover it from knowing equivariant objects once you keep track of the action of rep G on this category of equivariant objects. So it's a very useful theorem. Okay, so that's an example of something which is one affine. But, so now I want to give an example of something which is not one affine and which will play a very important role in the sequel. So I want to return to this example over here. So now let's take our y to be b squared gamma, where gamma is a finite abelian group. So up here we described the category, the two category of sheaves of categories. So we said that sheaves of categories over b squared g, b squared gamma is just vector spaces graded by the Cartier dual group. And so now let's see what the right-hand side is. So, however, if you compute quasi-coherent sheaves on b squared gamma, you'll just see vect. So the right-hand side will be just categories. And this functor, what it does, so it's global sections on b squared gamma. It takes that category graded by gamma check and extracts from it the degree zero part. So this functor, sorry, it's I should say dj cat. So dg cat gamma. It's categories acted graded by gamma check. So it's a functor from dj cat gamma to dj cat that takes a collection of categories kind of indexed by gamma check and sends it to just the degree zero component. So this functor is hugely non-conservative. So it's a well-defined functor, but it's not an equivalence of categories. So the point is that BG for G is an algebraic group is one affine, and B squared gamma is not one affine. All right. So the last kind of preparatory step that I'm going to perform before we launch into the two Fourier transform, let me make a recap about gerbs. So let's A be an abelian pre-stack. So an A gerb, I'll denote it by this script G sub A on Y. Y is an arbitrary pre-stack. Is this by definition the same as a map from Y to B squared A? When I write B squared, I implicitly sheafify in whatever topology you choose, let's say et al. So that's what gerbs are. So now I want to make a remark specifically about gerbs with respect to GM. So let's recall the following construction that, so if you have a line bundle, L on Y, which is the same thing as a map from Y to BGM. And if you have a sheaf, quasi-coherent sheaf on Y, you can create the tensor product. You can write L tensor F. And it's a new quasi-coherent sheaf on Y. And so there are many ways to view this construction. For example, you can do it just by gluing from the check datum. So and locally on Y, L tensor F is isomorphic to the digital F, but globally, of course, it's not. Like, for example, if you take global sections of F and global sections of L tensor F, they have nothing to do with each other. One can be 0 and another can be non-zero. So again, this is a local operation which looks very different, which makes a huge difference once you take global sections. And in the parallel way, so if you have a gerb with respect to GM on Y, and if you have a sheaf of categories C underlined on Y, you can perform the same kind of twist. And obtain a new sheaf of categories on Y. And again, when you take global sections, so you can take this C, and you can take global sections of this tensored up category. They may look very different. So it's an operation which is locally trivial on the source, but it becomes non-trivial after you take global sections. They're very dissimilar. All right. So now I'll introduce the object which will be of interest for us. So X will be an algebraic curve, as before. So gamma will be a finite abelian group. Consider the space are called gerbs with respect to gamma on X de Rham. So in other words, it's a mapping stack from X de Rham to B squared gamma. And I'll be interested in studying sheaves of categories over this thing. So that's what at the very beginning.
Yeah.
So it's that X de Rham. The beginning of first hour, like home from S to X de Rham is home from S reduced to X.
Okay.
It's that guy. So this is what we want to study. So you have to first understand how gerbs with respect to finite abelian group on a curve look like. So it's basically you're studying a Tal cohomology of your curve, or in this case, de Rham cohomology of the curve, actually, Drum doesn't really matter because gamma was finite. So Étale cohomology of X with coefficients in gamma. And if you choose a point, you can split it. So if you consider this, again, Drum really does matter because gamma is finite. Will be a little bit non-canonically isomorphic to the following. It will be B2 gamma times B H1 Étale on your curve times H2 Étale on your curve with coefficients in gamma, which we should remember is the same as gamma with the Tate twist -1. And so we kind of gave the description of sheaves of categories for each of the terms. So the upshot is that sheaves of categories of the space of gerbs is the same as the following. It's a datum of a category. So it's a category C equipped with the following pieces of data. So it's a sheaf of categories over B gamma, B2 gamma, but we said that this is the same as a category graded by gamma check. So grading by gamma check. So the last piece of data is a grading by gamma Tate twist -1. And the middle piece of data is an action of this finite group H1 Étale of gamma. And all these pieces commute. Again, so what you give yourself is a category which is really split. It is split as a direct sum of subcategories indexed by pairs, an element of gamma check, an element of gamma of -1, and each of these pieces is acted on by this finite group, which is H1 of the curve with coefficients in gamma. And so the final remark that I'll make today is the following, is that if you swap gamma with its Cartier dual of 1, you're going to see the exact same thing. And you also take into account Verdier duality. So this description will make it manifest that when we consider sheaves of categories over gerbs on the curve, we're getting the same two category for group gamma and for its almost dual. It's almost because I'm twisting by applying the Tate twist. And so this observation will play a role when we set up our 2 Fourier-Mukai transform. All right, so I think I'll stop for today because there was a lot of abstract stuff, and you'll see what happens tomorrow.